Hi everyone. In this talk we want to study the metallicity dependence on the effective temperature of red supergiants. Our goal was first to obtain the effective temperature and luminosity of a sample of red supergiants in the galaxy WLM, which is a metal-poor galaxy that has a metallicity around -1. And we also want to compare these results with the Magellanic clouds. For getting the effective temperatures, we use the method in Davis et al. 2013, which is based on fitting the spectral energy distribution continuum regions. With these results, then we want to study the dependency on metallicity. We expect that for a higher metallicity, we are going to obtain a lower effective temperature. So once we have our observations, we want to also compare with what the evolutionary models from the Geneva group predicts. So this is an example of the analysis of the observations. You can see on the top left, in red is the spectra of a red supergiant in WLM. In black is the best fitting Marx models for this spectra based on the spectral energy distribution method. On the bottom is the residuals of this fitting, and on the right we have the parameters that we obtained, so the effective temperature and extinction, with their error contours. We repeat this process for all the red supergiant sample in WLM, but also we do this for the SMC red supergiants and the LMC because we want to have a completeness. Then we plot these effective temperature and luminosities in the HR diagram, as you can see here on the left. And we also compare it with the Geneva evolutionary tracks. There's the different galaxies with the three different colors, and you can also see two black dots, which those were problematic, so we did not include them in the analysis. With this, we then calculate the average effective temperature of our results, and we find out that for WLM, which is the most metal poor, the results are around 250 kelvins warmer. To know also if our sample is statistically significant, because we are only using 10 red supergiants for each galaxy, we then calculate and we then compare it with the full sample of red supergiants and prove that this is actually statistically significant. When we have our observations, we then want to compare with the predictions from models. What we do is, using the Geneva models with three different metallicities, we do a population synthesis analysis. So we simulate first a very big number of stars that follow the initial mass-Salpeter function, and then with this we assign them random ages. Then we select the ones that are in the red supergiant phase, and we obtain the effective temperature that the model would predict. With this we have different histograms, and we calculate the mean temperature of the histogram, and the errors are going to be the standard deviation. So you can see this here in this plot. In magenta we have what the simulations predict, the mean effective temperature and the errors of non-rotational models, and with yellow is the same but with rotational models. And then we compare it with our observation analysis. You can see that there seems to be an offset between observations and models, and we calculate that the probability that these models would look like the data is 10 to the minus 5. This means that this systematic offset cannot be random. So what we think is that this offset is due to a wrong assumption from the mixing length parameter in the models, because these models are assuming a solar mixing length parameter. But for massive stars, there's been also more studies, for instance, see Chan 2018 or Desar 2013, that they show that assuming a solar mixing length parameter for these massive stars is not accurate. And with this work, we can also give this evidence and compare it with observations. So, to conclude, should these models be reevaluated for massive stars? And I want to know your opinion, and thanks for your attention.